Hello there, dear students, and welcome to Stuck in Physics. My name is Deepak Kumar, and we are looking at a problem from May 25, paper 2, time zone 1. The question says a detector moves along a line connecting it to a stationary loudspeaker. Emitted frequency 1700, speed of sound 340, detected frequency is 1600. All right, state the direction of motion of the detector. Now, you can clearly see that the detected frequency is less than the original frequency. This implies that the separation between the detector and the loudspeaker is increasing. So the detector must be moving away from the loudspeaker. Calculate the speed of detector. Now it's a Doppler effect question. We have the received frequency of 1600 hertz. This equals to 1700 times, there's a whole lot of things that go into the bracket. So in the numerator, we will have speed of sound minus the speed of detector, the listener, divided by the speed of sound, and this loudspeaker is at rest, so nothing else goes there. We just have to solve for this. So we'll move to the calculator. All right. So we are solving for V. So let's just quickly clear all of this. Okay. We are solving. We'll need N solve. Okay. N solve 1600 shift equals to 1700 times, have an entire bracket where we have 340 minus the variable x represents the V variable, which is the speed of detector, and in the denominator we have 340 again, and in the end we'll just close the brackets. Oh wait, we have to indicate what variable are we solving for. This that's x, and then we close the bracket, and then we can solve it. Again, warning, you can ignore it. So we get one solution that says V equals to 20 meters per second. That's it. That's the answer to part A2. Moving ahead, a loudspeaker and a detector, and the detector are now stationary and above the water surface. The loudspeaker is at point L, detector at point D. L and D same height. Sound reaches by two routes, one along LD and the other along LPD. Okay. Some data is given to us. Calculate the wavelength of sound in air. Fine. So for that part, we can use wave speed equals to wavelength times frequency. The wave equation. Wave speed is given as 340. 340 equals to wavelength, which is not known to us, times 1700, and lambda equals to 340 over 1700. This is like 20 over 100, so that's like 0.2 meters. So lambda equals to 0.2 meters. Fine. Outline why sound from L undergoes destructive interference at D. Now, for this part, we will have to recall the condition for destructive interference. Now, if you remember, the destructive interference can be found out, like when we can see or check if a certain point destructive interference takes place or not by looking at the path difference and the wavelength. So I know that delta x equals to n plus half lambda for destructive interference. We have the wavelength, that part is known to us. Delta x is the path difference. So for calculating the path difference, I see that from L, the source, sound reaches D via two routes. There's one that directly goes from L to D, that distance is 0.7, so 0.7, and the other route is LPD. The triangle LPD itself is an isosceles triangle, so the other two sides are 0.5 and 0.5. So the total distance along this path, LPD, is 0.5 plus 0.5, which is 1. So 1.0. You take the difference of this will be 0.3 meters. So that's delta x. Path difference is 0.3. So 0.3 equals to n plus 0.5 into 0.2. Now, we are implementing the condition of destructive interference. If at all the value of n comes out to be an integer, that will confirm that we are looking at a point of destructive interference, right? So you can directly say n equals to 0.3 over 0.2 minus 0.5, so that's 1.5 minus 0.5, so that's 1. N equals to 1. It's a fairly simple calculation. We don't really have to do it on calculator or anything. It's up to you, your convenience. So n equals to 1. Since we got the value of n as an integer, this indicates that point D is a point of destructive interference. Now, for the next part of the problem, we have to determine if the sound wave can enter water at point P or not. So, here's what we're going to do. We look at the sound wave, actually not the light wave, the sound wave traveling from L to P, and then we have to check if the sound wave will refract into water or not. Well, the best way to check that is implement Snell's law. Okay, so for that we will need the angle of incidence, so we'll just have to draw a line perpendicular to the air water interface. Remember, whenever we have to measure angles, be it reflection or refraction, along the interface, I mean, you need to draw a normal perpendicular to the interface exactly at the point where the ray is incident. Once you have that done, then you can measure the angle with respect to the normal, always. So this angle is to be calculated. Let's say this is theta. So this length will be 0.35 meters because half of 0.7. And I can say sine theta is 0.35 divided by 0.5. Let's leave this as it is because we don't need the value of theta exactly. We can just use the value of sine theta. That is what we're going to use. So if you recall Snell's law, it looks something like n1 over n2 equals to sine theta 2 over sine theta 1. This equals to v2 over v1. We just need to work with this part, right? So I can say sine, we have the speeds, right? So sine theta 2 over sine theta 1. Now, theta 1 is the angle of incidence in the first medium, so that's sine theta. So that's 0.35 over 0.5. Equals to v2 over v1. Now, v2 is the speed of sound in water, which is 1500, divided by the speed of sound in air, which is 340. Now I just have to solve for theta 2. So we'll bring back the calculator. All right, and solve again. Sine, wait, are we at degrees? Yes, you have to make sure that you're on degrees or radians as per the requirement of the problem. Fine. So we are already at degrees as it has been indicated here on the calculator. So I am solving for solvent, and then I need sine x divided by, there's another fraction in the denominator which is 0.35 over 0.5, and then this is equal to 1500 over 340, and we are solving for x, and then we close the brackets, and one of many solutions exit no solution. Well, when you see that you are implementing Snell's law and you're solving for an angle, calculator says no solution, that implies a refraction would not be possible. As simple as that. So since theta 2 has got no solution, or this equation itself has no solutions, sound wave will not enter. Wave doesn't enter at P. As simple as that. So I hope you guys understood that pretty well. If you've got any doubts, do let me know. The comment section is always open, and thank you for joining. I'll see you in the next one. Goodbye.